Hey there, class. Welcome to another kind of chemistry experiment. And, you know, with it being winter time here, I thought we'd talk a little bit about heat. For, my kind of Midwest self here at Central Illinois, we've had some days here recently in February where it's been, 0 degrees Fahrenheit even. I know we've been, extra thankful and blessed with warm homes and businesses and things like that. So I thought we'd talk a little bit about how things, can get warm and kind of the science behind that. And we'll do an experiment. But before we get any further, we should probably talk about specific heat. And what we're going to do is we're going to kind of look at the formula here. We'll kind of talk a little bit about that. And then we'll, do an experiment where we're going to see just a vivid difference between the specific heat of various, or well, not various, but two different substances, air and water. I know that we're all familiar with warmed objects, with warm air, with a hot stove perhaps. I mean, we've touched that and gotten some blisters. We've touched tables and things like that. And all of these different surfaces have different specific heats. So the heat or thermal energy required to raise the temperature of that particular material 1 degree. So let's see, let's pull it up here. We're going to take a look at the equation for that. So there we have it. So what we're going to, let's talk about that a little bit. So Q is the specific, or is the amount of heat, and M being, the mass, C being specific heat, and T being change in temperature. And kind of with that, if we take water, for instance, water has a specific heat, so amount of energy required to raise it 1 degree. But if you take, let's say the ocean versus a cup of water, it's going to take considerably more heat, considerably more thermal energy to raise the temperature of the ocean 1 degree versus a simple cup of water, due to the not even comparable change in masses. So with that being said, let's kind of dive into the experiment a little bit here. And so over here to my left, I've got one balloon filled with just air, and I've got one balloon filled with air and water. And what we're going to do is we're going to light them on fire. I know we got some pyros in here who want to see some fire. So we're going to do that today, and we're going to kind of observe the differences in the response to the flame, and we'll kind of talk about kind of why that is. So let's see here. All right. I hope that my neighbors don't get too upset with me here. Hopefully this isn't a loud kind of pop here. But this is one that's just water, or I'm sorry, just air. This is just air. Okay, not too bad. Just a squeaker. So that took, like 3 seconds, maybe? Alright, so this is the one. You can maybe kind of see the shadow in there a little bit, that there is some water in there. Let's do the same thing here and see what happens. Well, toss her up, folks. All right. Yeah, nothing happened there. I got a little bit of a warm warmish balloon, I guess. But the difference here is the specific heat of air versus water. And if you were to pull up a table, you would see that water's specific heat is about 4 times that of air. So it takes about 4 times as much energy to warm the water 1 degree as it does air. So, I mean, eventually, our water and air-filled balloon would bust, just for a simple fact of the material integrity becoming compromised. But I think we've really kind of demonstrated something pretty cool here. We took our air-filled balloon. It busted here within a couple of seconds, and then we applied the same heat to a balloon filled with water, which is a different heat capacity, and I still have a dry floor. So I would say come back next week for another chemistry experiment.